Well, good day, ladies and gentlemen, and you're all very welcome to this fortnight's session, technical session of the CNPS. Now, today we're continuing with this series of lectures that have been kindly prepared by Vladimir Netchitailo. I hope I haven't made such a mess of that pronunciation. Vladimir has a very interesting model which is concerned with Hypersphere. It's a sort of non-Euclidean system, Hypersphere world universe model. And 2 weeks ago, he gave us the first presentation, part one, which was basically on the medium, the medium of space. Now, today, he's continuing with this, and he's going to talk about multi-component dark matter. And as usual, every 2 weeks, the technical session is hosted by me, Ian Cowan, and Roger Anderson with Franklin, who usually undertake to accommodate us in the other weeks. So basically, it's actually a series. Just to remind you, it's a series of 8 parts because it's quite an extensive lecture. And we were toying with the idea of maybe doing it in bits and pieces, but then we realized that it's actually an integral whole, and it would be better if we did it in a series. Now I think we have one break actually, which is in 2 weeks' time, but we're continuing on until the summer with the 8 parts. That's our excuse me. That's our intention. So today we're concentrating on multi-component dark matter, and some of the things that Vladimir will be dealing with will be dark stars, which were proposed by John Mitchell, actually, who isn't very well promulgated, but in 1783. Review of history of dark matter, introduced multi-component dark matter system, and weak interaction between dark matter particles. Now, what the spiel has basically said, that multi-component dark matter system and weak interaction between dark matter particles, propose Macroobject Shell Model, give experimental results of dark matter signatures in gamma-ray spectra. So this whole question of dark matter, which is one of the elements, the other being dark energy, which many of us dissidents take issue with. Well, I think Vladimir will be giving us a different conception of his ideas with regard to dark matter, dating back, I suppose, to a postulation of some sort, which bears no resemblance to what is in the mainstream today, but it dates back to John Mitchell's work in the late 18th century. Okay, so that's an introduction. Now, I don't think it's too late in the year for me to remind you of the funding mechanism that the CNPS has. Just with your permission, I'll just put up David DeHilster again, just to remind you that the worldwide membership that we have is very much appreciated, and the membership dues are paying a certain percentage of the running costs, but they're not covering all. So we're trying to supplement that, and I think actually he's reached something like in excess of 50% of the target. So let me just play this very brief video before we start. If I can find it here now. Here it is.
Hello, my name is David DeHilster, and I'm president of the John Chappell Natural Philosophy.
Click twice, perhaps.
Hello, my name is David DeHilster, and I'm president of the John Chappell Natural Philosophy Society. Our organization is unique in the world in that we allow for serious criticisms of mainstream science, from physics to cosmology and from math to philosophy. And today, this organization resides 100% online. If you enjoy our Saturday morning talks, our websites, and the community of amazing critical thinkers you can interact with on the internet, then please consider contributing to our annual fund drive. It costs almost $3,000 per year to keep our internet presence and our Saturday morning talks alive and well. I want to thank all of our members who pay monthly and annual memberships, which is vital to our day-to-day operations. But unfortunately, this is not enough. And that's why we're looking to raise $2,000 in our 2024 drive. So if you don't want this organization to disappear and you think that its mission is important, then please consider donating to the CNPS. It's vital to keeping science moving forward. Please go to fund.naturalphilosophy.org and donate today. Thanks once again from all of us at the CNPS. Your donation is vital.
So thank you very much for that. And I'd like to acknowledge, the enthusiasm of everybody, including our speaker in coming in during the Easter holiday period and giving this lecture. We don't tend to disappear very much. I think we had lectures around the Christmas period and New Year, not actually Christmas Day or not New Year's Day, but just around that time. We didn't break. So once people are interested, we go ahead. That's fine. So again, the format is basically very similar to what we had 2 weeks ago. We'll have up to an hour, the speaker, and Vladimir again, I think, has prepared the text so we can read it on the screen, and he's going to go through it fairly slowly. He might actually go even slightly slower than he did the last time, because I think there were 1 or 2 comments back. But there will be an hour basically after that for questions and answers, and also maybe fuller discussion. So I'll bring people who are in on the green room. I see a few people in already in the green room, and I'll bring them in, whether they volunteer or not, possibly. But I do encourage the people on the Facebook and the YouTube perhaps to try to indicate some specific questions. I mean, you're using the chat literally as a chat between yourselves and saying, oh, the weather is very bad in this part of the country and blah, blah, blah. And fine, I don't gainsay that. Go ahead and do it. But if we could have a few questions, you might say, specific question for Vladimir, and we can then address it, because there's a danger otherwise that I'll miss it. I go through, and you're not, your audio isn't available as the audio is of the people in the green room. So just make sure that if there are any questions, you say this is a specific question. And furthermore, if it's a very, very urgent specific question, we prefer to wait until the end to discuss all these matters and have Q&A after Vladimir's finished. But if there's any very, very urgent question in extremis, we will interrupt the speaker, and he will be prepared to take it. So we prefer not to do that, but we will do it. We won't keep you waiting if there's anything really urgent that you're completely confused. So I'm going to give the floor to Vladimir now. I'll bring him up. You had to share your screen, didn't you, Vladimir, the last time?
Yes, I can.
So I might just stay here just for a moment, just to make sure it works, because it worked perfectly the last time. But there have been innumerable times when we had problems with other speakers. So I think what you have to do is share the thing, and then I have to put it up. And then I'll put my... Yeah.
Okay.
So say present, whatever it is, maybe your screen. It's at the bottom of the banner there, the center.
One sec, I'll do it.
Yeah, take your time.
Okay.
I just the problem is, if I put myself down and then I start speaking, you won't hear what I'm saying. So I just wanted to make sure that everything's all right. I'm sure you could do it without me, but that's one of the problems with moderators. The moderator would be fairly, I might say, blamed if something goes wrong. So I do take responsibility for it.
I'm sorry.
No, there's something
One
coming there.
sec. I don't know. One sec. I've done it before I joined you. That's it. Simple as this.
Yeah, you could forget in 5 minutes. You see present. Well, then it'll say, do you want to present the slides, or perhaps
Yes,
share
I know.
screen?
I know for sure what to do. Don't worry.
Yeah.
I know.
Okay.
One sec. It will be okay now.
I mean, I've done it a number of times, but I forget from time to time how to do it. And of course, just while we're doing that, just to remind everybody what I think is generally known, that the recording of this video will be available immediately after presentation. So you can go through it again, you can pause it at any point, you can rewind. Okay, so I see your presentation there. Let me put it up. It's up there now. Now, people should really maximize that by clicking in the bottom right-hand corner. There's a little sort of cut square there.
I don't know. I got my with the scale too. You know, it's a 200 right now. That's why I hope that it's okay for people too.
Yeah. See, I can take my own photograph away, but I can't really take yours, because then we won't have your video, your audio. I think there is a way of getting your audio, but I'd like to have your video as well. So whatever happened the last time, I'll get rid of myself now, and I think you can, if you have to increase it.
It seems to me I increased to the maximum. It's acceptable for people, because this is exactly
that's exactly whatever you did there. It filled the screen. I'm not sure how you did it, but you got rid of your own photograph, and at least temporarily, I think that is the way to do it, because otherwise people will say it's too small. Okay.
So Ian, you can go ahead and still keep people in the conversation. You just have to full screen one of the layouts, like I do here.
And you do that.
Hear you. So as long as you haven't removed someone from the stage, you can still talk and they can still hear.
Okay, I think you mentioned that before, and I had forgotten. So it's the three little dots on that presentation. You pull that down, and you say, "What do you say?"
Well, it's not that. It's that if you want to have one screen full screen, you just select the left-hand icon on each picture says full screen layout, and that will select who is full screen. Like if I select you full screen, the other people like Vladimir and myself can still speak even though we're off screen. So just to let you know that people who are off screen can still be participating as long as they're highlighted blue and on stage, everyone can hear. So
that's a useful yeah, that's very useful. Nevertheless, I will bring myself down so that I can cough and I won't have to mute myself. But I'll realize that when we finish the lecture, Franklin. So thank you for that tip. So Vladimir, we're all removed now, and we'll come back whenever you need it.
Okay, can I start?
Yes, please go ahead and start, Vladimir.
Okay. Hello, everyone. Thank you for coming. Let's continue. Today, it will be multi-component dark matter. First of all, I would like to stress that Hypersphere world as a model of a finite universe was proposed by Riemann in 1854. World universe model follows this idea, albeit proposing that the world is stretching and filled with the medium consisting of stable elementary particles. Let me remind you the main results of the first presentation, medium of the world. Microwave background radiation, intergalactic plasma, far infrared background radiation speak in favor of existence of medium, which is an absolute frame of reference. Time, space, gravitation are closely connected with impedance, gravitomagnetic parameter, and energy density of the medium. There is no medium, there is nothing. Critical energy density of the world can be found by the Hubble's law. There is no need in general relativity. Medium consists of stable elementary particles, protons, electrons, photons, neutrinos, and dark matter particles. The relative energy density of dark matter particles is about 92.8%, and ordinary particles about 4.8% in the medium and 2.4% in macro objects. Maximum value of the velocity of electromagnetic waves equals to the value of the electrodynamic constant C. The most important gravitational and Hubble's parameter depend on the energy density of the medium, which is a homogeneous and isotropic. Thanks to revealed by Wurm interconnectivity of cosmological parameters, we show that the gravitational parameter that can be measured directly makes measurable all cosmological parameters which cannot be measured directly. Summary of the calculated by Wurm in 2013 cosmological parameters and experimentally measured parameters are presented in the following table. We emphasize that Wurm allows for precise calculation of values that were only measured experimentally earlier, like ambient temperature, far infrared background temperature, peak, and makes verifiable predictions with the other cosmological parameters like gravitational, Hubble's, ionized baryons, minimum photons energy. You can compare these two columns, calculated and measured values, and years when it happened. Dark stars. The basic feeling of many physicists is that dark matter does not exist because they believe that the dark matter constant was erroneously created due to a false analysis of the expected rotational velocity of stars in the outer range of spiral galaxy, and also presumably due to a lack of knowledge about other evidence for dark matter. In the following presentation, I will concentrate on a dismissal of this belief. I will provide a short review of the dark matter history for 240 years, in which great scientists were involved. John Michell was an English natural philosopher and clergyman who provided pioneering insights into a wide range of scientific fields, including astronomy, geology, optics, and gravitation. Considered one of the greatest unsung scientists of all time, he is the first person known to have proposed the existence of dark stars and the first to have suggested that earthquakes travel in seismic waves. The American Physical Society described Michell as being so far ahead of his scientific contemporaries that his ideas languished in obscurity until they were reinvented more than a century later. The Society stated that while he was one of the most brilliant and original scientists of his time, Michell remains virtually unknown today, in part because he did little to develop and promote his own path-breaking ideas. In the paper for the Philosophical Transactions of the Royal Society of London, read on 27 November 1783, Michell was the first to propose the existence of dark stars. Michell suggested that there might be many dark stars in the universe and proposed that astronomers could detect dark stars by looking for star systems which behaved gravitationally like two stars, but where only one star could be seen. Michell argued that this would show the presence of a dark star. It was an extraordinarily accurate prediction of binary systems in which a dark star and a normal star orbit around the center of mass. In the Milky Way galaxy, there are a dozen such binary systems emitting X-rays. Please pay tribute to this genius physicist. The first known binary system was Cygnus X1, identified independently by several researchers in 1971, 188 years later. Can you believe it? It remains among the most studied astronomical objects in its class. The compact object is now estimated to have a mass of 21.2 mass of the Sun's. Cygnus X1 is about 5 million years old. Though highly and erratically variable, Cygnus X1 is typically the brightest persistent source of hot X-rays with energies up to 60 kiloelectron volts. Bessel, Lord Kelvin, Poincaré, Zwicky, and many other great scientists discussed various aspects of dark matter. The hypothesis of dark stars was developed by well-known scientists Ripamonti and Abel, Spoler, Fries and Gondola, Fries, Randler, Diller, and Spoler and Valur. In 2020, Genzel and Guess were awarded the Nobel Prize in Physics for discovery of a supermassive compact object at the center of our galaxy. This discovery confirmed one of the most important predictions of WOMB in 2013. Macro objects of the world have cores made up of the discussed dark matter particles. Other particles, including dark matter and baryonic matter, form shells surrounding the cores. The first phase of stellar evolution in the history of the world may be dark stars powered by dark matter heating rather than fusion. Ely, Pauling, and Fries in the article Supermassive Dark Star Candidates seen by GWST wrote, the first generation of stars in the universe is yet to be observed. There are two leading theories for those objects that mark the beginning of the cosmic dawn: hydrogen burning population 3 stars and dark stars made of hydrogen and helium but powered by dark matter heating. We show that each of these following 3 objects, JADIS GS Z13, Z12, and Z11, are consistent with a supermassive dark star interpretation, thus identifying for the first time dark star candidates. Dark galaxies. A truly dark galaxy is an isolated cloud consisting only of dark matter. In some scenarios, it is possible that some optically dark objects may contain enough atomic hydrogen, Hi, that a blind Hi survey would detect them. A good example of dark object is the southwestern component of the binary system known as Hi 1225 plus 01, discovered by Giovanelli and Haynes in 1989. While the northeastern Hi component hosts a small star-forming dwarf, the southwestern component has no detectable stellar counterpart. It is not an isolated object, being part of an apparent binary system. Initially discovered in 2000, Virgo Hi21 was announced in 2005 as a good candidate to be a true dark galaxy. Minchin et al. In the article 21 centimeter synthesis observations of Virgo Hi21, a possible dark galaxy in the Virgo cluster, say, many observations indicate that dark matter dominates the extragalactic universe, yet no dark structure of galactic proportions has ever been convincingly identified. Previously, we have suggested that Virgo Hi21, a 21 centimeter source we found in the Virgo cluster, was a possible dark galaxy because of its broad line width, about 200 kilometers per second, unaccompanied by any visible gravitational source to account for it. We have now imaged Virgo H121 in the neutral hydrogen line and find what could be a dark edge-on spinning disk with the mass and diameter of a typical spiral galaxy. Moreover, Virgo H121 has unquestionably been involved in an interaction with NGC 4254, a luminous spiral with an odd one-armed morphology. We have also used the Hubble Space Telescope to search for stars associated with H1 and find none. The best telescope None. The cloud is at the Virgo cluster's distance of 52 million light years. It is roughly 50 kilolight years across, about half the diameter of Milky Way starry disk. The strength of 21 centimeter emission indicates that the cloud harbors 2 multiplied 10 to the power 7 mass of the suns of atomic hydrogen, about 1/10 Milky Way supply. But the cloud's total mass is much greater, implying that, like most galaxies, including our own, it consists primarily of dark matter. Astronomers estimated the cloud's mass at least 9 multiplied 10 to the power 10 mass of the sun. Xu et al. Obtained HI mass 8.3 multiplied 10 to the power 7 mass of the suns of this galaxy. Their findings provide observational evidence that this galaxy is an isolated dark dwarf galaxy. This is the first time that an isolated dark galaxy has been detected in the nearby universe. A galaxy G0613 plus 52 has about the same characteristics of mass and gas content as a normal spiral galaxy. There are no galaxies within 112 megaparsec, making it a pretty isolated target. O'Neill et al. Found that it is an incredibly gas-rich galaxy. It is not demonstrating star formation like we'd expect, probably because its gas is too diffuse. At the same time, it's too far from other galaxies for them to help trigger star formation through any encounters. It appears to be both undisturbed and undeveloped. This could be our first discovery of a nearby galaxy made up of primordial gas. This is an artist's depiction of hydrogen gas observed in galaxy G0613 plus 52. The colors indicate the likely rotation of the gas relative to the observer: red away, blue toward. The question is, where did this hydrogen gas get an angular momentum? In the case of this galaxy, 8.8 billion light years away, a radio signal, 21 centimeter line, was magnified by another galaxy acting as a lensing body. Roy said that this effectively results in the magnification of the signal by a factor of 30, allowing the telescope to pick it up. At the conclusion, binary galaxy systems, including dark galaxies, were discovered. HI 1225 plus 01 by Giovanelli and Haynes in 1989. Virgo H121 with NGS 4254 by Minchin et al. In 2000. Prediction of John Mitchell of the existence of dark stars is valid for dark galaxies also. 21 centimeter emission. The 21 centimeter line refers to a forbidden transition in the neutral hydrogen atoms. It is produced by a spin flip transition, which means the direction of electron spin is reversed relative to the spin of the proton. The electromagnetic radiation producing this line has a frequency of 1420 megahertz that is equivalent to a wavelength of 21.11 centimeters and a transition energy 5.874 microelectron volts. This line has a very low transition probability, so it requires large amounts of hydrogen gas for it to be seen. According to Padovani et al., small amounts of atomic hydrogen detected as absorption dips in the 21 centimeter line spectrum are a well-known characteristic of dark clouds. The abundance of hydrogen atoms measured in the densest regions of molecular clouds can only be explained by the dissociation of hydrogen molecules by cosmic rays. Then two questions arise: where cosmic rays came from, and how to explain broad line widths about 200 kilometers per second of 21 centimeters source. Mondal and Barkana in article Prospects for Precision Cosmology with the 21 centimeter signal from the dark ages say, while exotic physics could be discovered, here we quantify the expected benefits within the standard cosmology. A measurement of the global sky average 21 centimeter signal to the precision of thermal noise from 1,000 hour integration would yield a measurement within 10% of a combination of cosmological parameters. Precision cosmology with 21 centimeter fluctuations requires a collecting area of 10 square kilometers, corresponding to 400,000 stations. Is it reasonable or not? It seems to me unreasonable. Galactic rotation curve. In 2021, Ludwig, in his paper, Galactic Rotation Curve and Dark Matter According to Gravitomagnetism, wrote, most theories used to explain the rotation curve have been restricted to the Newtonian potential framework, disregarding the general relativistic corrections associated with mass currents. In this paper, it is shown that the gravitomagnetic field produced by the currents modified the galactic rotation curve, notably at large distances. The effects attributed to dark matter can be simply explained by the gravitomagnetic field produced by the mass currents. I would like to stress this conclusion. A developed womb is based on gravitomagnetism. The explanation of the galactic rotation curve made by Ludwig is in a good agreement with the approach of womb. We emphasize that gravitomagnetism considers not only interactions between masses, but also between mass currents, producing gravitomagnetic field. Equations for gravitomagnetism were first published in 1893, before general relativity, by Oliver Heaviside as a separate theory expanding Newton's law. We don't know history of physics at all. Sorry. Superclusters. Galaxy clusters are particularly important for dark matter studies. Mass to light ratio of the Virgo superclusters is about 300 times larger than that of solar ratio. Similar ratios are obtained for other superclusters. These ratios are main arguments in favor of presence of significant amounts of dark matter in the world. Masses of superclusters can be estimated in two independent ways: from the scatter in radial velocities of the galaxies within clusters. Gravitational lenses can measure cluster masses without relying on observations of dynamics. It is experimental results. It was imaginations. That's why it is experiments. Sorry. Multi-component dark matter. Basic ideas. It is the main goal of WOMB to develop a model based on two-dimensionless parameters only: the dimensionless Rydberg constant alpha and the time-varying parameter q, which is a measure of the size and age of the world. We often use well-known physical parameters, keeping in mind that all of them can be expressed through the basic units. Taking the relative values of physical parameters in terms of the basic units, we can express all dimensionless parameters of the world through the parameters alpha and q in various rational exponents, as well as small integer numbers and pi. In our view, there is no way to prevent an occurrence of the initial singularity in Big Bang model. A finite world must have gotten started in a principally different way, a fluctuation in the eternal universe with an extrapolated finite size that equals to the basic size unit of A. The size of this fluctuation can increase with a finite c gravitodynamic constant. Then there is no need to introduce cosmological inflation. However, a question about the mechanism of continuous creation of matter in the world arises, according to whom the eternal universe is the creator of the world's dark matter particles, which must have constant rest energies. In 1952, Nobel laureate in physics Nambu proposed an empirical mass spectrum of elementary particles with a mass unit close to 1/4 of the mass of a pion. He noticed that meson masses are even multiplies of a mass unit m0/2, baryon and also unstable lepton masses. The odd multiplies and mass difference among similar particles are quantized by 70 mega-electron volts, in whom we introduce a basic energy unit E0 that equals to 70 mega-electron volts, where H is the Planck constant. It is worth noting that the rest energy of electron equals to alpha E0, and the Rydberg unit of energy equals to half alpha cube E0. R is the Rydberg constant. Considering the main goal of whom two-dimensionless parameters only, the rest energies of dark matter particles should be proportional to constant alpha only. Indirect effects in cosmic rays and gamma-ray background from the annihilation of cold dark matter in the form of heavy stable neutral leptons in galaxies were considered in pioneer article by Nobel laureates in physics Lee and Weinberg in 1977, whom follow this idea. According to whom the world consists of dark matter, about 92.8% of the total matter, and ordinary matter, about 7.2%. It means that dark matter should play the main role in any cosmological model. It is the case in whom an ordinary matter is a byproduct of dark matter particles' self-annihilation. In our opinion, it is high time to make a paradigm shift for dark matter cosmology and classical physics. Dark matter particles. Following the mechanism discussed by Boehm et al., we proposed multi-component dark matter system consisting of two couples of co-annihilating dark matter particles, a heavy dark matter fermion, DMF1, 1.3 tera-electron volt, and a light spin zero boson Dirac, 70 mega-electron volts. That is a dipole of Dirac's monopoles with charge mu equals E/2 alpha. E is the elementary charge. A heavy fermion DMF2, 9.6 giga-electron volt, and a light spin zero boson LOP, 340 kilo-electron volt. That is a dipole of preons with electrical charge E/3. DMF3, 3.7 kilo-electron volts, DMF4, 0.2 electron volts, and boson Xion, 5.3 microelectron volts. In frames of whom dark matter particles DMF1, DMF2, and DMF3 have rest energies, which corresponds to rest energies of neutralinos, WIMPs, and sterile neutrinos discussed in literature. DMM4 constitute the biggest shell of dark matter cores of superclusters. Dirac, which is a magnetic dipole of Dirac's monopoles, is introduced to explain the Dirac's quantization condition. The quantum theory of magnetic charge started with a paper by Paul Dirac in 1931. In this paper, he showed that if any magnetic monopoles exist in the universe, then all electric charge in the universe must be quantized. The electric charge is in fact quantized, which is consistent with, but does not prove the existence of monopoles. Since Dirac's paper, several systematic monopole searches have been performed, but it remains an open question whether monopoles exist. In our opinion, all electric charges are quantized due to the existence of dipoles of Dirac's monopoles, which are the smallest building blocks of the structure of constituent quarks and hadrons, mesons, and baryons. A lobe, which is an electric dipole of preons with the rest energy 1/3 of electron energy, is introduced to explain all subatomic particles with electrical charge proportional to E/3. Preons are the smallest building blocks of the structure of quarks and leptons. According to D'Souza and Kalman, in particle physics, preons are postulated point-like particles conceived to be subcomponents of quarks and leptons. We didn't consider binding energies of Dirac's envelopes, and thus the values of their rest energies are approximate. They have negligible electrostatic and electromagnetic charges because the separation between charges is very small. They do, however, possess electrostatic and electromagnetic dipole momentum. Xion is an analog of axion discussed in literature. It has the value of the rest energy of 5.3 microelectron volts. Axion is a hypothetical elementary particle postulated in the Pecky-Quinn theory to resolve the strong CP problem in quantum chromodynamics. With a rest energy about 5 microelectron volts, axions could account for dark matter and thus be both dark matter candidate and a solution to strong CP problem. In our view, xions are responsible for the lethargic mechanism of gravitation, in whom gravity is an emergent phenomenon. The reason for this multi-component dark matter system is to explain the diversity of very high energy gamma ray sources in the world, the diversity of dark matter cores of macro objects of the world, superclusters, galaxies, and extrasolar systems, which are fermion compact objects and dark matter reactors. Wurm postulates that rest energies of dark matter fermions and bosons are proportional to the basic energy unit E0 multiplied by different exponents of alpha and can be expressed with the following formulas. We still don't have a direct confirmation of dark matter particles' rest energies, but we do have a number of indirect observations. The signatures of dark matter particles' self-annihilation with these expected rest energies are found in spectra of the diffuse gamma ray background and the emissions of various macro objects in the world. We connect observed gamma ray spectra with the structure of macro objects, nuclei, and shells compositions. Self-annihilation of those dark matter particles can give rise to any combination of gamma ray lines. Thus, the diversity of very high energy gamma ray sources in the world has a clear explanation. In this regard, it is worth recalling a story about neutrinos. The neutrino was postulated first by Pauli in 1930 to explain how beta decay could conserve energy, momentum, and angular momentum spin. But we still don't know the values of neutrino masses. Although we still cannot measure neutrinos' masses directly, no one doubts their existence. Neutrons serve as another example. The mass of a neutron cannot be directly determined by mass spectrometry since it has no electric charge. But since the masses of a proton and of a deuteron can be measured with a mass spectrometer, the mass of a neutron can be deduced by subtracting proton mass from deuteron mass, with the difference being the mass of a neutron plus the binding energy of the deuterium. Dark matter particles do not possess an electric charge. Their masses cannot be directly measured by mass spectrometry. Hence, they can be observed only indirectly due to their self-annihilation and irradiation of gamma quants. We will discuss it below. Distribution of Wolf's energy density. Our model holds that energy density of all types of self-annihilating dark matter particles is proportional to a basic proton energy density unit in the medium, rho p, in all times, that in the present epoch equals to this equation. It's about 4.8% of the whole matter, where rho critical is the critical energy density of the world. In all, there are 6 different types of dark matter particles. Then the total energy density of dark matter particles is 28.8%. That is in a good agreement with results of the literature. The total Xion energy density is about 64%. The total baryonic energy density is about 7.2%. The sum of electron and microwave background radiation energy density equals to this value. We take energy density of neutrinos equal to MBR energy density. For far infrared background radiation energy density, we take this value. Then the energy density of the world equals to the theoretical critical energy density. From this equation, we can calculate a value of 1 over alpha using electron to proton mass ratio, which is in excellent agreement with the commonly adopted value. It follows that there is a direct correlation between constant alpha and this ratio, expressed by the obtained equation. As shown, this ratio is not an independent constant, but is instead derived from alpha. I wanna mention now that there is no dark energy in my model. As the conclusion, the world's energy density is inversely proportional to the dimensionless time-varying parameter Q in all cosmological times. The particles' relative energy densities are proportional to constant alpha. Macroobject Shell Model, in whom macrostructures of the world, superclusters, galaxies, extrasolar systems have nuclei made up of dark matter fermions, which are surrounded by shells composed of dark matter and baryonic matter. The shells envelop one another like a Russian doll. The lighter a particle, the greater the radius and the mass of its shell. Innermost shells are the smallest and are made up of the heaviest particles. Outer shells are larger and consist of lighter particles. We developed a theory of fermion compact objects. A proposed weak interaction of dark matter particles provides integrity of all shells. Table 1 describes parameters of macro objects cos, which are 3D fluid balls with a very high viscosity and function as a solid-state objects. The calculated parameters of the shells show that nuclei made up of DM1, DM2 compose cores of dark stars in galaxies and normal stars in extrasolar systems. Shells of DMF3 and electron-positron plasma around nuclei made of DMF1 and DMF2 make up cores of galaxies. Nuclei made up of DMF1 and or DMF2, surrounded by shells of DMF3 and DMF4, compose cores of superclusters. According to whom, cores of galaxies are dark matter compact objects made up of DMF1, DMF2, with shells of DMF3, with the calculated maximum mass of 6 multiplied 10 to the power 10 mass of the Sun. This value is in a good agreement with the experimentally obtained value of the most massive black hole ever found, with a mass of 6.6 multiplied 10 to the power 10 mass of the Sun, at the center of Ton 618. It is worth noting that there are no black holes in WOMB. Dark matter particle signatures in gamma-ray spectra. Dark matter particle self-annihilation is proportional to the square of the dark matter density, and it's especially efficient in places of highest concentration of dark matter particles, such as the compact stars built up from fermionic dark matter particles. By definition, X-rays are emitted by electrons outside of the nucleus, while gamma rays are emitted by the nucleus, in whom the self-annihilation of dark matter particles gives rise to gamma radiations. Physicists working in the field of X-ray and gamma-ray astronomy attempt to determine masses of dark matter particles which would fit experimental results with the developed models. WOMB has principally different approach. The model predicts existence of multi-component dark matter system consisting of dark matter particles with these values of rest energies, and look for signs of a self-annihilation of these particles in the observed gamma-ray spectra. We connect gamma-ray spectra with the structure, core, and shells compositions of macro objects. In frames of WOMB, no macro objects are made up of just a single type of dark matter particles, since other dark matter particles, as well as the baryonic matter, are present in the shells. It follows that macro objects irradiate gamma quants in different spectral ranges with ratios of fluxes depending on structure of a given macro object. DMF 1.3 tera-electron volt. Chavez et al. Have found that a significant fraction of galactic very high energy gamma ray sources do not appear to have obvious counterparts at other wavelengths. In frames of WOMB, the correlation between kilo-electron volts and tera-electron volt emission can be easily explained by the self-annihilation of DMF3 with 3.7 kilo-electron rest energy. Counterpart, in the shell around the core of active galactic nucleus, made up of DMF1, 1.3 tera-electron volt. Lack of a counterpart in gamma-ray spectra means that DMF3 shell is too small to be observed. A detailed analysis of interpretation of latest data of different collaborations in terms of dark matter annihilation and decay in various propagation models showed that for the Fermi lot and Hess data, dark matter particle mass is 1.3 tera-electron volts. The obtained data by other collaborations require dark matter particle mass to be around 1 to 1.5 tera-electron volt, which is in a good agreement with the predicted mass of DMF1, 1.3 tera-electron volt. Look how many references I have. The presence of spectral break at 1.3 tera-electron volt in very high energy spectra was measured for different blazars. Some nearby sources have unique signatures in the tera-electron region. Broken power law at 1.3 tera-electron volts. The dark matter interpretations of the electron-positron excess observed by Pamela, Fermi, and Ethics suggests the dark matter particle mass of 1.3 tera-electron-volt. Look at these publications. DMF2, 9.6 giga-electron-volt. Hooper summarized and discussed the body of evidence which has accumulated in favor of dark matter in the form of approximately 10 giga-electron particles, including the spectrum and angular distribution of gamma rays from the galactic center, the synchrotron emission from the Milky Way's radio filaments, the diffuse synchrotron emission from the inner galaxy, and lower energy signals from the direct detection experiments Gamma, Libra, Cocaine, and CREST-2. It is worth noting that a similar excess of gamma rays was observed in the central region of Andromeda Galaxy 2. McDaniel found that the best fitting models are with the dark matter mass 11 giga-electron volts. Based on IGRET observations, Sri Kumar et al. Attribute very high energy emissions to blazars. Most of the measured spectra of individual blazars only extend to several giga-electron volts and none extend above 10 giga-electron volts. One proposes that cores of blazars are composed of self-annihilating dark matter fermion 2, 9.6 giga-electron volt, explaining why no observed radiation extends above 10 giga-electron volts. Dirac, 70 mega-electron volts. Hunter discussed a peak of 67.5 mega-electron volts. Below 100 mega-electron volts, gamma rays produced via electron bremsstrahlung and the dominant component of the observed spectrum, whereas above and about 100 mega-electron volts, the gamma rays from pion decay are the dominant component of the spectrum. 70 mega-electron volt peak in IGRET data was discussed by Golubkov and Khlopov, who explained it by the decay of pion meson produced in nuclear reactions. Wolf et al. Said that gamma rays at 70 mega-electron volt are detectable by glass and IGRET. Yamazaki and Nakamura attribute this peak in the emission spectrum from the old supernova rendered to pion decay. Note that whenever the 70 mega-electron volt peak appears in gamma-ray spectrum, it is always attributed to pion decay. We claim that pion decay produces the 67.5 mega-electron volt peak, while Dirac's self-annihilation is responsible for 70 mega-electron volt peak. To find out the source of the observed broad peak about 70 mega-electron volts, we suggest utilization of exponentially cut-off power law, as usual, for analysis of experimental data for gamma-ray energies less than 70 mega-electron volts. A better fit of experimental data will be evidence of Dirac's self-annihilation. ELOP, 340 kilo-electron volts. Existence of dark matter particles of similar mass, less than 0.42 mega-electron volts, has been discussed by Rassera. The experimental 100-400 kilo-electron volt bump discussed by Jarsky is in a good agreement with the theoretical analysis of Rassera et al. And with self-annihilation of dark matter particles allows. Gruber et al. Describe a wide gamma-ray extracollective background spectrum between 1 kilo-electron volt and 10 kilo-electron volt, and conclude that the fit required the sum of 3 power laws. According to whom, the fit of the total diffuse spectrum in the range between 3 kilo-electron volt and 10 giga-electron volt should be performed based on 3 exponentially cut-off power laws with injection spectral with this equation with the spectral index gamma and E cut being the cutoff energy of the source spectrum. For values of E cut, we should use 9.6 gigaelectron volt in the range 9.6 gigaelectron volts, 7 megaelectron volt range, 70 megaelectron volts in the 70 megaelectron volts, 340 kiloelectron volt range, 340 kiloelectron volts self-annihilating LOPs in the 340 kiloelectron volts, 3.7 kiloelectron volt range. They fit in the range between 9.6 gigaelectron volt and 1.3 teraelectron volt, should be done with E cut 1.3 teraelectron volt. DMF3, 3.7 kiloelectron volts. The very first signature of the emission around 3.7 kiloelectron volts was found in 1967 by Gorenstein et al. They found that the highest number of net counts is recorded in the beams centered at 375 kiloelectron volts. An important result was obtained by Safi Harb and Ogelman in 1997. They reported the observations of the X-ray lobes of the large galactic source W15. A broken power law model gives the best fit. The power law indices gamma are 1.9 and 3.6, with the break occurring at 3.7 kiloelectron volt, as Wum proposed. Ito analyzed the broadband 3 to 550 kiloelectron volt spectra of NGC 4388 and found line-like residual around 3.7 kiloelectron volts at the high confidence level. In 2012, Moretti et al. Measured the diffuse gamma-ray emission at the deepest level and with the best accuracy available. Emission line around 3.7 kiloelectron volts is clearly visible in the obtained spectrum. DMF 4, 0.2 electron volts. Unidentified infrared emission bands are infrared discrete emissions from circumstellar regions, interstellar media, star-forming regions, and extragalactic objects for which the identity of the emitting materials is unknown. They are, in fact, the fingerprints of all galaxies. The main infrared features occur around peaks at 3.3, 6.2, 7.7, 8.6, 11.2, and 12.7 micrometers, with the photons rest energy at these peaks with this value, and respectively. This phenomenon has been studied for about 45 years. The prevailing hypothesis that the materials responsible for this phenomenon are polycyclic, aromatic hydrocarbon molecules, which are thought to be one of the main forms in which carbon exists in space. And yet, not a single member of this group of compounds had been identified in space definitely until now. Can you believe in so complicated chemistry in the whole universe? In whom, by analogy with electron-positron annihilation, we suppose that particles DMF4 and BDMF4 self-annihilate with the emission of 2 or 3 gamma quants. Indeed, the self-annihilation of them follows an energy conservation requirement. 2 BDMF4 particles with the rest energy 0.38 electron volts can produce 2 gamma quants with this energy 3.3 micrometers. 2 DMF4 particles 0.199 electron volts can produce 2 gamma quants with energy 0.2 electron volts that corresponds to 6.2 micrometers wavelengths. 2 DMF4 particles can produce 3 gamma quants with energies equivalent to 7.7 micrometers 8.6 micrometers, 11.2 micrometers, and 12.7 micrometers. Xeon, 5.3 microelectron volts. Concentration of xeons, the rest energy 5287 microelectron volts, inside of dark matter clouds is considerably larger, 5 orders of magnitude, than in the intergalactic medium. They are ultra-relativistic particles and have total energies larger than the rest energy up to this value, 5.87 microelectron volts. A self-annihilation of an ensemble of xeons with energies around 5874 microelectron volts produces 21 centimeter radiation with broad line width about 200 kilometers per second. In frames of whom there is no need in hydrogen atoms, for which there is no explanation for a mechanism of their production. Dark galaxies are made of dark matter particles only. Conclusion. Dark matter is abundant. 2.4% of ordinary matter is in superclusters, galaxies, stars, planets, etc. 4.8% of ordinary matter is in the medium of the world. The remaining 92.8% is dark matter. That dark matter is omnipresent. 2/3 of the total dark matter is in the medium of the world. 1/3 of the total dark matter is in macro objects of the world. Dark matter reactors in cause of all gravitationally rounded macro objects. Wurm predicts existence of dark matter particles with these rest energies. We should concentrate our efforts on the observations of cosmic gamma rays with spectral lines corresponding to the predicted values of dark matter particles' rest energies. In our view, great experimental results and observations achieved by astronomy should be analyzed through the prism of Wurm. Astronomers should plan new targeted experiments based on the results of this analysis. Considering the GWST discoveries, successes of Wurm, and 86 years of Dirac's proposals, it is high time to make a paradigm shift for dark matter cosmology and classical physics. As usual, acknowledgments. I'm always grateful to academician Prokhorov and Professor Malenko, whose influence on my scientific life has been decisive. I'm eternally grateful to my scientific father, Paul Dirac, who was a genius and foresaw the future of physics in a new cosmology. I'm forever grateful to Nikola Tesla, who was a genius. I'm much obliged to Professor Korda for publishing my manuscripts in the Journal of High Energy Physics, Gravitation, and Cosmology. I'm very grateful to Nick Percival for his useful comments and suggestions, which have led to an overall improvement of the presentation. Special thanks to my son Ilya, who helped me clarify the model and improve its understanding. Thank you so much for your attention. I'm ready to answer all your questions. Bye now.
Thank you very much. And let me see. I'll just bring down the presentation just for the moment. Right. And as usual, you didn't disappoint. You've more than covered the subject that you undertook to. And there have been a number of questions coming in, which I'm trying to keep an eye on, as well as looking at your detailed presentation. And we have a number of people in the green room. Perhaps I can just once more avail myself of the moderator's privilege by just saying a few words without hogging the conversation. Okay, so actually, it would appear that you're conceiving of Riemann as being very forthcoming in his earlier ideas that the universe is non-Euclidean. Actually, I think it was Cornelis in one of the questions here who said, well, I think he was sort of assuming that the universe is Euclidean, and therefore he was saying, well, if you have a non-Euclidean, a hyperspace, it's merely a mathematical model. So you might be able to say something about how, you know, we've dismissed maybe the universe as being merely Euclidean. I just had one or two other things, just maybe while I have the floor. Yeah, so basically, as far as I can see, and you can confirm this or deny it, you conceive of dark matter as constituting more than 90% of the universe, and you know that would be consonant with the general view. Now, I have looked at some aspect of this before, and I've tried to explain it. That if and you might want to comment on this as well, Vladimir, in a quick answer.
Okay.
But if you conceive of the speed of interaction of gravity to be different from that of light, I mean, the general sort of general theory of relativity would say, well, it's the same as the speed of light. But if you conceive that it has a much greater speed. In fact, it's effectively infinite with regard to the speed of light because it's orders of magnitude more. Well, if you conceive of that and you consider the universe and you consider a position in space which is so many light years away, well, the only way that you can observe either by light or by electromagnetic radiation something to be in that area is if it emitted such radiation the same number of years before your observation as the number of light years it is away. Because if it emitted some radiation prior to that, well, the light hasn't reached you; it's gone right past you. And if it emitted radiation subsequently, well, the light is still on its way to your eye, or the radiation to your detector, and you haven't seen it yet. So, but we could perhaps find that there's some gravitational effects, some dynamical effects, because you're conceiving of these effects as occurring much more rapidly. So I just wanted to know what you thought of those ideas. Just to summarize again, because I've put about 3 points to you very quickly. One is the non-Euclidean Riemannian type, system. Is that merely mathematical, or if not, observationally? The dark matter business, you seem to be in agreement roughly with the proportion that the mainstream would consider. And what do you think about this snapshot idea? Because again, another question from Quest, I think, was he was saying, how is it that we don't see it? Is it invisible, or are we seeing through it? You might just address some of those 3-4 quick points before we get to
Okay, too many questions at once. Let's start one by one. First of all, if you will see some light, it means that you can see electromagnetic phenomenon, light. That's why whatever going with gravitation, it doesn't matter. We can see only what we can see, electromagnetic waves. All of them, they have a maximum speed equals to the gravity dynamic constant c. That's it. Simple like this. The second question is hypersphere. Of course, Riemann, he was a mathematician. He proposed this idea of the world, hypersphere world, as a mathematician. And I saturated this mathematical hypothesis with the physical parameters. I mean, the medium, macro objects, and the spreading of this sphere, hypersphere. Why? Because we know that there is some spreading of the galaxies, of the stars around us. That's why we should explain in some way. Hypothesis of hypersphere world is very important for my model, because we have continuously accepting new dark matter. How to have a homogeneous saturation of our world by the surrounding universe. How? This is only one way to have a hypersphere and to saturate our world with new dark matter particles continuously. This is a very important point for hypersphere world. As for the gravitodynamic parameter C, I suppose that it is equivalent to electrodynamic constant C. There is no proof of it, of course, but it's a model, and in this model, the expansion of the 4D ball is going with the speed equals to the gravitodynamic constant C. And all the results, what I've got based on this supposition, it is very good experimentally confirmed. I showed you the table 1 with all these parameters had the same up to 5-6 digits after the comma, the same values. Later, after I calculated these cosmological parameters in 2013. It seems to me I answered all the couple of questions. I don't know, maybe I missed something. Please remind me.
No, I think you did. You addressed those points, and I think maybe our difference at the moment is that I would ascribe to gravitational waves the same principles and properties that you've been talking about, but I'm sort of making a hypothetical distinction between gravitational waves and gravitational interaction. But anyway, that might be something we can come back to.
Let me tell you a few words. Heaviside in 1893, he started with electromagnetic Maxwell equations, and he put the same equations for gravitomagnetic constant, the same C, everything's the same. That's why analogy between electromagnetism and gravitomagnetism, Heaviside put in equations with the same value of C, gravitation parameter too. I mean gravitodynamic constant C. That's why, I'm following history of the physics. My main concern was, what? We don't know history of physics. For myself, I opened so many genius people, so many great scientists, and we missed all of them. Our contemporary physicists, they don't know, maybe forgot all these extraordinary results, like John Mitchell or somebody else, It's unbelievable for me how bad we know history of physics and how many genius ideas we missed. And what is my proposal, my model, is the main goal of my model, is to collect all these genius ideas forgotten by contemporary physicists in one ensemble, in one model, and they will play all different. It will be one orchestra, and the model is like a conductor of this orchestra to play with all these ideas, with all these instruments at once. This is my main idea.
Yeah, and it's quite impressive. Obviously, the results of your analysis and the precision of the agreement with the experiment is impressive. But in your acknowledgments alone, you've actually made it clear that a number of people, your scientific fathers and so on, like Tesla and all the others, these are very prominent individuals. And for my part, you've brought to my attention John Mitchell, whose work I wasn't familiar with, but actually that's much interesting.
Unfortunately, nobody else, not only you. I didn't know about him too. I'm very sorry, man. It's not
you don't know about what?
We are bad, because we have different history of physics,
Well, that's true, and sometimes it can become a bit nationalistic. Like one group claims the induction coil or something like that, or Henry's work versus Faraday or something. But okay. So let's spend a little time just trying to capture some of the questions, because I did invite people specifically to ask questions, and some of them did. A lot of discussion here, which we don't have time to go into, but it's valuable all the same. So I think we've dealt. We've probably dealt with Cornelis's idea, because I said it was an adjunct to my own point about the hypersphere. But he's a bit more pointed than I am. He said, could Vladimir make clear that the theory is not a physical theory, but is a mathematical model, since it uses non-Euclidean geometry? Well, presumably you're saying that actually the world is non-Euclidean. Isn't that so? So maybe you've answered that already.
Our world, no. Let me tell you, our world is hypersphere, but in a not so far away from us, it's Euclidean, no doubt. It's so close because radius of this hypersphere so huge that we cannot even think about it. And we know about this radius of curvature only based on this Q parameter. This is the witness of our curved feature of the world, Q. All the parameters depending on Q is the witness of this curvature. That's it. But the radius of curvature is 10 to the power 26 meters. That's why in all our real life, in all our even galaxy, there is no difference between this hypersphere and Euclidean, geometry and Euclidean space, what we have in mind. But in principle, of course, it's a hypersphere in a faraway distances. That's why, there is no contradiction with Euclidean space.
Yeah, which would accord with our normal observations in daily life.
It's a normal observation. It's a normal Euclidean space, but the distance is up to r. This radius of curvature, it's 10 to 26 meters. As you can use Euclidean space as usual, no problem. The curvature you can feel, even suppose that the Earth curvature of Earth you can see only in the far distances, 100 kilometers.
So this 10 to the 26 meters, do you know offhand, what would that roughly be in, say, light years?
In light years, it is 14.22 billion light years.
Okay.
14 billion light years. That's why we have something like 1 light year. It's our solar system. Our sun, our solar system, it's about 1 light year. That's it. 1 light year and compare with 14 billion light years. That's why in our galaxy, of course, we can use our standard mathematics, standard Euclidean space.
Okay. Which coincidentally is about the area that the conventionally accepted Big Bang theory, would say that the world or the universe started that many years ago.
No, because Big Bang model suppose that this explosion, I don't know what happened, it was 13.77 billion light years. I have extra 0.45 billion, about 500 million light years, dark epoch, to get my dark matter objects, to accumulate tremendous, huge angular momentum. I will talk about this issue in the next presentation. No, it's totally different story. And what is important? They calculated this age based on some experimental results with macro objects that have only 2.4% of matter. And my calculations of the age of the world based on the calculations of the measurements of gravitational constant. It's an absolute age of the world. There is no dependence on any phenomenon, on any material in my model. You measured your gravitational parameter, and you can find Hubble's parameter, age of the world, radius of curvature, all these parameters you can find at once based on gravitational constant, which can be measured on the Earth. That's it. That's why my age of the world longer, 500 million light years. And what is important, it's an absolute age of the world. Doesn't depend on anything. Don't even compare with Big Bang model. It's a two different stories, you know. We don't need Big Bang model. We don't need all this, you know, obsolete theory. We don't need it. We must replace it. We must do movement to dark matter cosmology and astrophysics.
Right. It's just that it's of an order which is not too dissimilar. Whereas some of us might consider that the universe is infinite in time, you know, as well as space. So that would be a contrary view. But just take this quest thing again. I think you may have dealt with this, but he's sort of asking, what is the nature of the reason that we can't see dark matter? You know, in one of H.G. Wells's books, The Invisible Man, actually, it is, it was quite a scientific theory. He talked about scientists interfering with the refractive index of materials and making a man invisible so that he would be there. You could touch him, but you couldn't see him. So I don't know if there's a simple answer to question, why can't we see it? Are we seeing through it, or is it...
Let me, I gave you already in my presentation two examples. We cannot see neutron. How do we know that it exists? Because there is no charge. We can see only matter with electric charge. If there is no charge, we cannot see it. We calculated mass of neutron. The same story with neutrinos. We don't know even neutrinos mass. We have some squared, some numbers. We think that it's a neutrinos. We have our model. We calculate some parameters of the neutrinos, but we don't argue that they don't exist. That's why you can see something by your eyes, what matter, what has this electric charge. If there is no charge, there is nothing to do. There are no electromagnetic waves, because what we can see, electromagnetic waves. And if there is no electromagnetic, then we cannot see anything. I'm sorry.
Okay. So it's not sensible to our investigations. Cornelis has asked, what is the size of each dark matter particle, or are they point particle quantizations of the background of energy density? I'm not sure if you've dealt with that already.
Let me tell you my understanding. You know, he asked the question from quantum physics. I'm talking about the classical physics. In classical physics, there is the minimum size 10 to the power minus 14 meters. Whatever is less size, you cannot even tell about the size, because all the issues, all the space, time, gravitation, we can tell only when we have our medium of the world, when we have bigger size than 10 to the minus 14 meters. That's why classical physics, it has limitation, minimum size 10 to the minus 14 meters. For quantum physics, as my opinion, there are no such even parameters, space, time, size, and all this stuff. I don't know how to name them, points, not points, because you cannot introduce even these classical notions like space, time, coordinates, size, and also. These are the classical notions we can use only when we have the medium. We don't have medium, we have nothing to do about it. That's why even the question, what is the size of proton, electron, and all this stuff, it's not nonsense, of course. We cannot ask this question. We cannot even ask this question because we are classical objects. We live in a classical world, and classical world starts when the medium of the world arises, and that's it.
Okay, so your ideas are more revolutionary. Franklin has asked, is the dark star, this is presumably the Mitchell type idea, the same thing we know as black holes? But probably not. What would you say?
Of course not. Of course not. Black holes, in my opinion, black holes don't exist. I will tell you why. We have initial singularity. I'm trying to avoid initial singularity. And then let's start with black holes, additional singularities. Because what does it mean, the black hole? At the center, you have point. In this point, concentrated all the gravitational mass, and all the rest area around, it's empty. We don't have it. I'm a physicist. I don't like infinities at all. Instead of one infinity of our initial singularity, we compose many dark matter objects, in my opinion, and we name them black holes. What are the evidences of the black hole? What are the black hole experimental results? We name it. Even this, this Nobel laureate in physics, Genzel and Gert, they named the supermassive compact objects at the center of Milky Way galaxy. They didn't name it black holes. Black holes, it's some kind of, interpretation of their results. But in my paper, I showed all the test results, all the experiments. They prove that it is dark matter object. In one of my following presentations, I will talk in detail about Milky Way galaxy and the center of Milky Way galaxy. I cannot tell everything about in one presentation. Sorry. That's why
furthermore, presumably, Vladimir, in later presentations, you'll be dealing with things like dark energy as well.
No, there is no dark energy. It's invented to explain some effect, acceleration of expansion. It's wrong. It's absolutely wrong.
But even to say that, well, you've said it now, but you will maybe remind us of that. I agree with that myself, by the way, but you will maybe
dark energy doesn't exist. You cannot do any conclusions based on experiments with our standard ordinary method. Especially, we have only 2.4% of method, and we have a few some objects. 20, 30, so very low quantities of these objects. And they belong to different superclusters. They're moving against each other in any way. I talked in the first presentation about that. I will talk about this in details later. The next presentation will be about macrostructures formation, and I will tell you what's going on. And we cannot compare one galaxy to another galaxy belonging to different superclusters. And even in one supercluster, some galaxies moving out of our galaxy, another one going to us, Andromeda galaxy. Why it moves to us, to Milky Way galaxy? Why? How to explain in Big Bang model moving of these two close galaxies to each other? There is no explanation. And do you know how many blue shifted galaxies we have in the world? Over 8,300 galaxies moving toward us. How to explain these results in a standard?
Plus the most near one, isn't that true? The Andromeda one.
Andromeda one, and no explanation. Everybody, it's okay. Andromeda will kill us in 10 billion years and all this stuff,
Right.
Mathematical tricks to talk about this issue, but I'm a physicist. I want to know if something is going up, explain me why.
Okay.
That's why forget about dark energy. There is no dark energy, and forget about all these experiments explaining accelerated expansion. No way. It's a different galaxies belonging to different superclusters, and they can move whatever you want. They can go out, they can go up and down. It's up to the real position of each galaxy in superclusters.
Well, it's important to get your strong statement on that. Now, I'm a little surprised, and we might bring Franklin in a moment. He's in the green room as well, but I'm surprised he said this. He said, we've directly imaged black holes and generally matched up with predictions. I think he's probably referring to the recent photographs, so-called photographs, maybe composite photographs of what are meant to be black holes.
You know, I know this picture, but it is not a black hole. It is a picture of some matter around the black hole, so named black hole. It's not black hole. You
It's
know,
like a ring.
interesting result that when in 1 year they've done the same picture, it was totally different. How come during 1 year of our experiments, this ring around the black hole, dark matter core in my case, in my model, changed so significantly? I don't know. That's why please have your patience. I have my presentation. I don't know, maybe it will be number 4 or 5, and I will explain you all the results about the Milky Way galaxy, including center of dark matter galaxy. That's why we'll
Yeah,
see. We'll see. Because I
I,
cannot
I,
tell you all the details right now because it's too much for one
yeah,
presentation.
and we have intimated that before, particularly with regard to some of the questions which had arisen from the first presentation. So I sort of expect that after your last presentation, there'll be a lot of questions, because in order to answer some of these questions, we have to wait. For example, your next presentation, as you say, will be on things like the angular momentum, for example,
And formation of a macrostructure.
and the
Yes.
formation of macromatter. Yes, quite so. So Franklin has come back. He said actually it probably it won't explain dark matter. So he sort of retrieved some of those ideas. Okay, so. Okay, I've just got a comment from Nick Percival. I have to leave a bit early, but I have to comment. So let's see, have we got him in time? Yeah, he's still here. So Nick,
Yes.
we have you now. You haven't gone yet. The floor is
Yes.
yours.
First of all, thank you very much, Vladimir. But CNPS is not really heavy in cosmology. So it's really a treat to have this fire hose of empirical evidence and many interpretations of this empirical evidence from some of the major figures in physics and astronomy. And this is just part 1 of 10. So thank you. I wonder if you could read the first paragraph of Dark Matter again. You don't have to put it up, just might read it.
You mean of this presentation?
Yes.
Okay, let me try to do it.
Your section.
You know, it's a very good paragraph, and I agree with you. Thank you so much for this reminding and your.
Yeah, I think it'll help a lot of people actually as well, just to have this revision of it.
Okay. One sec, I will go one more time. Sorry.
Take your time.
I closed before, but I will open it now. Don't worry. Yes, it takes some time because computer.
I have to put it up as well, so remember that.
Yes.
Yes, the first paragraph under dark stars. Yes.
I can read if you need. The basic feeling of many physicists is that dark matter does not exist because they believe the dark matter construct was erroneously created due to a false analysis of the expected rotational velocity of stars in the outer range of spiral galaxies, and also presumably due to a lack of knowledge about other evidence for dark matter. Is absolutely right. First of all, let me tell you, rotation curves explained by mass currents by Ludwig in 2021, and I'm so happy that at last it happens. That's why you don't need dark matter to prove it, to confirm. The next very important point, I gave you the knowledge history of dark matter for 240 years. The next question is very important. I provide you with all the experimental results confirming that dark matter does exist. I gave you the names of the great scientists, Paul Poincaré, it doesn't matter, Lord Kelvin, and all of them, they were involved in these dark matter investigations. They are not crazy. I used, the ideas of our Nobel Prize laureate in physics about the annihilation of dark matter, and so on and so on. As I told you, my main goal was to collect all these great ideas in one picture and to be a conductor of this orchestra. That's it. That's why take a look. Even today my presentation, most of it experimental results confirming existence of dark matter.
So to the CNPS audience, who might initially have been put off by the mention of dark matter, I would just say that, I will repeat what Vladimir just said, or refer you to what Vladimir just said. It's based on the empirical data. But also, he's getting away from general relativity and black holes, which I agree, anything based on a singularity doesn't seem to be like physics to me. And he's going back to a replacement for relativistic cosmology to a cosmology that's based on classical physics. So that should appeal to a lot of people within the CNPS. And let me just ask you one question that's kind of related to that. You talk about neutrinos in sort of as a minor role, but there is a feeling among many in the CNPS community that neutrinos came about because Fermi made an error in his calculations. So that's sort of like parallels the point about dark matter. Don't dismiss all of this incredible amount of information about cosmology just because we have a bias against, or some might have a bias against neutrinos. But you might also comment about your views on neutrinos as well. And that's my final point.
Thank you so much for a very good question. It's not only CNPS Society, but some other guys, they don't believe in the existence of neutrinos. Yes, I know about it. What is important? I'm so happy to be a classical physicist. What I mean, to work with classical notions, with classical world, and cosmology, it's a classical physics. Quantum physics, when we are talking about some single objects like neutrinos, proton, electron, and so on, it's a quantum physics. As for me, quantum physics needs maybe different even approach against what we have right now. And I don't know what kind of approach. As for me, it should be some kind of revolution, maybe in quantum physics too, because what we have right now, we have a lot of questions, we have a lot of problems with the single objects, and I don't know anything about all of them. I introduced neutrinos only as a witness that we cannot measure. It doesn't mean it doesn't exist. Maybe it is exists, maybe not. But what about the neutron? Neutron. We have no physics without neutron at all. We don't have any chemical elements. Nevertheless, we calculated its mass. We don't have it at all. That's why I can miss neutrinos. If it's questionable, it's okay. For my cosmology, it doesn't matter because it is quantum physics. And I hope that some experts in quantum physics will answer all these questions. Do you believe in neutrinos or not? Maybe it will be some specialist in this physics, in this quantum physics, and he will give us the arguments about why it exists or it does not exist. I will be more than happy to meet such guys who can explain me quantum physics. I'm not expert in quantum physics at all. As for me, it's even more complicated than the whole universe, the whole world in my world medium. That's
Well,
why
take Feynman's words. Anybody who understands, thinks they understand it, doesn't.
That's
So,
why
Nick,
quantum physics, it's a very complicated. You know, even notions in quantum physics, all of them from classical physics. All these parameters, the Planck constant and alpha and all this stuff, you know, they came from classical physics. We have our equations based on some dimensions, some time, you know. I don't understand. Schrödinger
Eulerian.
equation, I don't understand it because these notions, time and space, they don't exist in quantum physics. They don't exist as for me. You can name it, you can introduce them only in classical physics. That's why what will happen to quantum physics, I have no clue.
Thank you. Excellent answer to my question.
Well, thank you very much, Nick, for that intervention. It's brought a number of important points to our attention. Actually, one of the indications that we've had an all-absorbing lecture today is that the time has just flown and the questions have come in, and Vladimir has been valiantly dealing with them. So, unfortunately, I think all we could do before maybe summarizing and finishing off is to allow one more participant in the green room to have a brief conversation if he wishes to. I'm sorry not to ask everybody, but we just don't have time today. So if there's anybody who wants to come in for a couple of minutes, we have time for that. Otherwise, we can just go to the summary. No, Franklin and James. I see John Hodge and Cornelis are the cameras are off, but if they want to come in for a moment, if anybody would. Franklin, Franklin, just very briefly, because we did briefly deal with your ideas, and it seemed to be a bit contradictory, I know, and so on, about the dark matter. And so have you anything else to say, or do you think we've...
Well, Vladimir, I wanted to ask you, because, you know, the very first things you said during your presentation was that, you know, there's this controversy over whether dark matter exists. And I thought you were going to present some arguments as to, you know, why those are not valid, because obviously if the whole concept of dark matter doesn't need to be explained, if you can explain the gravitational rotational curves without invoking dark matter, then it's like the rest of your presentation really wouldn't even make any sense. I mean, I understand that, you know, you've presented that there are these possible dark matter candidates, and you've presented some evidence showing, you know, that, you know, the observational things seem to exist, but still you have to deal with the criticisms that dark matter doesn't actually exist. I mean, the biggest one that I know of, which was brought up by David Hilster, was that spherical galaxies which have a spherical distribution, actually don't have any dark matter. This cannot be explained by any dark matter theory, since there's no reason why the distribution like that should prevent the formation of, say, your dark stars. So you would have to explain, why is it no dark stars exist in this spherical galaxy? Now, the main criticism is that the rotational galaxy curves are determined using a simplification that Newton came up with, which is that no matter how the matter is distributed in around, like, say, the solar system, in order to predict the actual orbital speed, you can presume that all the matter is compressed into a single location. Now, that's something which Newton came up, which is allowed due to the application of calculus. Now, the problem with that is that, once again, that is a simplification. What you should do is that in like a disk-shaped structure, as where we observe dark matter, you need to go and calculate each individual point and the gravity effect of, like, this one in the middle to the edge and this one to, like, the very beginning. You cannot simply just take all the matter and compress it into a ball and then do your orbital calculations like that. This is where the dark matter calculation actually comes from, because that's what they're doing. They're applying this massive simplification, and it causes the incorrect calculation of the orbital speeds of the objects which are in the outer edge. So, I mean, so I wanted to bring that up. I wanted to see what your reaction is. I mean, do you have a disproof of that particular objection?
Do you think that's reasonable or not, Vladimir?
Let me tell you, first of all, too many questions. I don't know which one to start answering to you, man. First of all, the principal point, dark matter exists. You know, I told you already many times that even in our supercluster, we have a supercluster, the ratio of mass to the light 300 times more than the ratio for our galaxy, Milky Way galaxy. And all superclusters, they have some dark matter core, huge one with a huge mass, with a huge angular momentum, and so on and so on. And what is important, today in my presentation, I showed you two independent experimental proof of existence of dark matter cores. First of all, behavior of stars around this core, like in our Milky Way galaxy. And the second one, gravitational lensing, even with dark galaxies. There is no galaxy and there is a gravitational lensing. That's why this is two confirmation of the existence of dark matter. The next very important point, I showed you in the first presentation 2 weeks ago that critical energy density can be calculated based on Hubble's law only. And when I calculated it, I told there is no general relativity. We don't need it to obtain this formula for critical energy density. And out of this critical energy density, only 4.8% in the medium, we measured it with fast radio burst, and 2.4% in our macro objects. Let me ask you the question. 92.8% of energy density of matter in the world, what it is? Because critical energy density calculated based on the law, only Hubble's law, and that's it. And you have so huge number against the ordinary matter we're dealing with. That's why, you know, there is no way we must put something for instead of this 92.8% of your matter inside of your model. It's dark matter in my case. The next point is about rotational curve. Let me ask you a question. I work with this cosmology for 22 years. I've done so much to put this model in one picture. And I cannot answer all the questions about the rotation curves, about something else. On the contrary, I invite all the physical community to take part in this new development of a new approaches to old phenomena, to old questions. What is important?
I would just encourage you to take as a new piece of information, very significant new piece of information, which is recently observed, that spherical galaxies have no dark matter. So your theory needs to take that into account. It's a new piece of information.
One step. Thank you so much. I will take a look on it. Maybe I will answer next time.
Very interesting.
But what is important, as for these galaxies, as for me, Ludwig done this job. He's the expert in this business. And I believe in him because what my main idea is, how to collect the existing experimental results in one picture. And gravitomagnetism I use all the time. And suddenly in 2021, the right guy with the right expert in this business answered the question, what is going on with these galaxies? And I'm happy about it because the first critics of dark matter is rotational curves. We don't need dark matter for rotational curves. We need it all in the centers of all macro objects, superclusters, galaxies, even our sun, our planets, our moons, all of them. Even our Earth, we have inside of us dark star. It's made of dark matter particles.
And we are, of course, all subject to our preconceived ideas. I mean, I've enunciated mine, which is that there's a very great difference between the speed of interaction of electromagnetic radiation and gravitational forces, and therefore I would claim that there are objects out in distant space for which we have mechanical forces, orbital forces or whatever, but we're not detecting electromagnetically. So I claim that dark matter doesn't exist. But I mean that's an extreme divergence from your own ideas. I'm sure, and I'm getting some comments in. I'm highly skeptical of dark matter as well for other reasons, and Franklin has given some. So thank you very much, Franklin. I dare say we'll be coming back to this, and maybe even troubling you, Vladimir, a bit more in the light of your next talks. So just before summarizing and officially closing the meeting, is there anything more you'd like to say, or have you said it all, or do you think some of the points have been raised are ridiculous, or will you be coming back to this as your next parts?
You know what? I can tell a few words, because inside of my presentation, I told most of my ideas and most of my desires, how to implement, how to execute some ideas, something to do. I'm so happy about astronomy at that time. We have so many different results, so much better than it was before, that I cannot follow even all the publications right now. It's impossible for one person. I invite all of you guys, if you have your interest in the development of my model, I will be more than happy to discuss with you the ideas, the hypotheses, my proposals, how to do the experiment, because I am alone right now. I cannot do myself all this new dark matter classical physics. In my 8th presentation, I will tell you about my new ideas about classical physics too. That's why, please consider the possibility for you not only to ask the questions, to answer these questions. And you can contact me directly. You can send me your questions, your emails, your information. Friend, please send me an information about this globular cluster of stars. I will take a look at it, because always you should have a very good experimental confirmation of it. And I want to prove it, because everybody right now believes that Milky Way galaxy has a black holes inside. It's wrong. It's absolutely wrong, because you must collect all the experimental results and to see the whole picture. The same story with your spherical, collapse of these stars. I don't know how to name it them. Please send me all the information, all your questions. I will be more than happy to answer them, because I'm so happy to have great interest in my model, in my presentation. I'm going to make change in all our information about the world, about the universe. I want to have a paradigm shift in cosmology. It's time. 86 years ago, Paul Dirac, he told it already about. Let's follow his ideas. He's not live right now. Let's do at least now, after 86 years of his expectations. Thank you so much for your interest in my work, for your good questions. It will increase my, interest in some issues. I will be ready to answer all your questions. It will induce some new ideas, maybe. I don't know. I'm always open for all the discussions about the cosmology. Thank you so much for your participation, for your interest, and good luck with you. And I will see you in 4 weeks with the next presentation.
Yeah, thank you for reminding that. And you've been exceedingly generous, not only in your time and in the effort, and indeed giving us this lecture at 7 a.m. your time in commencement on the day before Easter Sunday. But your offer of perusing any information that's given to you on any of these issues, which we have different ideas on, experimental ideas. It's admittedly very, very fundamental that you've come to the conclusion that the galaxies do not have a black hole in the center. That this is an erroneous concept altogether. That's very, very important. So I'd encourage you all to start thinking about this, and I think actually there is a bit of a consciousness of cosmology at the moment, because on Monday week, of course, we have the total eclipse of the sun. The most advantageous place to view this is probably North America. I had an invitation myself to go to a place called Grapevine in Texas, which is on the center line, to view the total eclipse on the 8th of April. But unfortunately, all the information only came in about 10 days beforehand, and I wasn't able to organize everything. So I think I'm going to have to skip it this year. I was at the last one in the United States in August of 2017. But anyway, if any of you, I think Franklin said in one of the emails that he was going to view it. So that might just keep your interest in the whole question of cosmology. And of course, Vladimir will be returning to this, because in 4 weeks' time, well, in 2 weeks' time, we have some other subjects, so a bit of a breather. And then Vladimir will be coming back to part 3, where he'll be going into details about his conception of the formation of macrostructures. And he'll be looking at things, as I said, like angular momentum. So, so this again is the theory and the practice and mating them together. So it's my pleasant duty. Unfortunately, the time has completely run out of us, and I must close the meeting now. But it's my pleasant duty once again to thank all the participants, to thank you for your questions and for your contributions, and most of all to thank our speaker, who has given up a large portion of his career. Actually, he's given 20 weeks or something of his time to give us these lectures in 8 parts, and he's done a very considerable amount of work, and it's actually quite encouraging, the results he's obtained, very accurate results. So he's not dismissive of experiment by any means. He's formulating a theory, and then he's making sure that it accords with experiment. Otherwise, it has to be ditched. So I would just once again ask you to have patience, and maybe to go through the lecture again, and to await the further parts. And Vladimir has promised us, and I have no reason to doubt him, that at the end of the 8 parts, there will be a sort of a whole which will sort of mate together, and we'll get a better idea, because some of the ideas can be a bit foreign to us. To me, I wasn't familiar with some of his ideas, but it's beginning to gel a little more. So I would ask you, to have patience, and maybe to persevere a little. As I said, we're very privileged to have Vladimir agreeing to do this, getting up so early every 2 weeks. And we look forward to seeing him, towards the end of April. So I'm going to end the stream now, and wish you all, wherever you are, a very good day and a very happy Easter. Goodbye.